So today we're going to try to attempt to explain special relativity. So just in case for people who haven't seen this before, I have done this whole series with James and Doctica. So if anyone wants to see those, I'm going to add a link. And here we're just going to cover, maybe not everything, but I didn't explain everything really well last time. So I'm going to try to improve it also based on some comments, that people had. And so in case you guys missed the first two episodes, the main idea is that the question, what if, space-time is something real? Not just some abstract mathematical geometry, but actually something real that has properties. And so the only thing really that we assumed is that, well, if it's something real and if it has to support transverse wave, it's got to have elasticity. So that's really the main thing we are, the main assumption right now. And I'm trying to keep it really simple and not add any more complicated things. I know there's been some comments that some people were saying, well, it can't be perfectly linear, right? And that's probably correct. But right now, all we've talked so far, general relativity and also the later episodes, we didn't really need anything else. And so I really want to keep it as simple as possible for as long as possible.
That makes sense.
Because otherwise, if you add it, then, you make it too complicated. And this is just really a one thing. It's elastic. Yeah. That's pretty much it.
And if you need to add something later, you just add something later.
Of course. Yeah. That doesn't mean I think
not a big deal.
Isn't anything more complicated. I mean, I don't know. I'm just trying to see how far can we get actually with this. So also, some people have a lot of hesitancy to think that space-time could be real. They go, oh no, it's conflicting standard physics. Well, let's, so for those people, what I could say, well, imagine we are writing a science fiction story from a parallel universe. And in that universe, there is a medium. And let's see how far we can take this story, right? Yeah. Maybe there's some point where it doesn't, work anymore and we have to throw it all out. That's fine. Yeah. But I think it's interesting to see how far we can get. So basically, when we have a elasticity, we have shear transverse waves, then we know, and of course, this material, whatever this is obviously not going to be any material we know. It's not going to be made of atoms. By definition,
definitely not. Definitely not atoms.
We don't, but still. So all the words I can use are the words that from real life, right? So I'm going to assume similar laws apply. So, for instance, what we know from real materials, which are elastic, is that the speed wave, the wave speed of a transverse wave depends on the shear modulus and the density. So that's the thing I'm going to use, right? Obviously, I don't have anything else. Yes. Formula in this context here, it just means stiffness, basically, how stiff the material is, basically. So the larger the number is, the stiffer it is. So steel is very stiff compared to a pudding, right? That's basically all it is. Yeah.
Okay.
And that's really the only thing the only assumption. Everything else kind of derived from that, because if that's the only thing, right, then, well, what is matter? What is light? Well, it's got to be derived from this somehow. So it's got to be some kind of wave, some kind of standing wave, traveling wave, some kind of defect. And we'll cover all this later. And in the previous episode, what we talked about that, well, if that's the case, then, if there's regions in the universe where the numbers here are different, so either you change the stiffness a little bit or the density a little bit, you get refraction. I think hopefully the light refraction was clear to everyone, but I know it was not clear about the matter wave. Okay. So I want to answer that question before we actually dive into special relativity. And just to be clear again, there's a lot of things we did not assume. So I did not specify what kind this is, if it's composed of anything smaller, if it's continuous. I just really don't know. And I'm not going to speculate. It's fun, but, I have no reason to speculate any of this. I don't know at all what kind of medium this is, if it's even.
Yeah. A lot of people ask that question. What is it? And
I don't know.
We don't need to, for the sake of this discussion, we don't need to
all I want to see, how far do we get, assuming there is something and it's elastic. That's pretty much it. So just to be clear about that. And sometimes words are misleading. Different people have different interpretations of words. When they say physical or medium, people would think, oh, I'm thinking of a crystal. I don't know what it is, right? So it's elastic. And as far from modeling perspective, so when you do the mathematical formulas, if it's discrete in some way, right? If it's granular, we couldn't detect it right now. So it's perfectly fine in math and in software to assume it's continuous, because the end result doesn't change. Whether you use this kind of thing, where it's some kind of granular structure, because if this is granular, it would be around Planck length or less even, and it wouldn't impact, say, the electron, at least from from all we are talking about, it's not going to matter, right? So you can have any model you like at all, it won't matter. But we can't conclude anything. So that's the main thing. And then just because I really like this simulation here, I want to show this one again. Like for normal materials, like ice or steel, diamond. Again, here's the formula. So this is basically the stiffness, as you were asking before. The thing at the bottom is the density. And so there's different values for different earthly materials. Like diamond is very stiff compared to steel. The density is different. And you can calculate from that the speed of the transverse wave. And just because I think it looks kind of cool, I just love that thing. So here, for instance, what we can do, we can, let me also change the wave type. This is some kind of gravitational wave now. And we can change, if you change the stiffness, if you change the density, that's we make it less dense, it will move the waves will move faster, right? And when we make it denser, it will move slower.
What is it about that motion that makes it a gravitational wave? What are the particle, what are the elements doing? Are they?
If you look at this, it's sort of expanding and contracting.
I see.
Well, I didn't write out the formula, but I'll share the link and then you can apply with this. Yeah. No,
they look really cool actually. I was just wondering, like I'm trying to figure out what the motion is that you say it makes a gravitational wave.
Well, this is just from standard public. This is all the formulas they use are really standard physics. So just to be clear, also for viewers, I'm not saying anything is. The only thing I think is wrong, in my opinion, in standard physics is the interpretation and the underlying explanation. I'm not.
Yeah, the math is fine.
As far as I know, I'm not contradicting any of the math. And if I do, it's a mistake of my end. So,
No.
Yeah. And so stiffness is this when we make it stiffer, it will also move faster. So if these springs here become stiffer, the wave will move faster. When we make it less stiff, like floppy, it will move slower, more slowly, right? So that's basically the idea of whatever that medium is. Now, there were some questions. Last time when we talked about general relativity, we talked about, refraction. And I think for light, I assume it was clear to everyone how that works. Because when you slow down, when you have let's just increase density as an example, the wave, if you have like a people marching in a lawn and you start to get into mud, you would slow down and then the light would also curve, the path would curve. But for so I had shown this simulation here for that sort of illustrate what happens with a matter wave, let's say an atom. And I was just kind of using some spiral, something that goes in a circle. And, in this case, we have a gravitational gradient, a density gradient or refractive index gradient is better. But it was not really, I think I didn't explain well why this should also, start to move towards the higher index. And I will try to explain this a little better, hopefully. Now, first of all, anyone interested, there are several papers that use normal materials, normal waves, that use that effect. For instance, there's this paper here where they have a plate and they can change the refractive index of that plate, I think electronically or something, I don't remember the details, and they can steer waves, elastic waves in that plate by using
I've heard that.
So that's pretty cool. There are other examples where they can get a wave, I think it's kind of like a Gaussian wave packet to move around by changing the refractive index. So this is not something totally new.
Real.
It's real. It's a real thing. There's another cool thing. This is called phononic crystal Lundberg lens, using elastic waves also. So there's like an aluminum plate with different holes, and the different sizes of the holes create like a refractive index gradient, and they can again steer the waves, and they can even focus waves in a certain point and extract energy from it, which is intriguing. Anyway, so I thought, because I think I like these simulations with the people.
The people, yay.
I'm trying to explain.
I like the people simulations.
The people. Yeah.
It kind of gives, I don't know, it gives you, a more tangible idea of what you're talking about.
I explained it to my daughter and she thought it was trivial. So hopefully it is understandable.
Was it trivial to implement?
Well, it take a while. I use AI to help me code.
Yeah, of course.
But to make sure it was correct. And
you have to tweak it and
But it's fun. I like to do that. So imagine you have a bunch of people marching in a circle. So let me just do this in uniform grass, just grass first. And, they try to maintain that circle, right? And I'm kind of overlaying, this is sort of an illustration of a matter wave, something like could be an electron, right? Something, a wave going in a circle or something like that. And they try to maintain that, that shape. Now, gradient. So now what happens, this is, imagine on the left side here, we have mud. On the right side, there's grass. So there's a gradient, okay? So the people here on the left side, they can't walk as fast because they get stuck a little bit in the mud. And so what happens is that they start to bunch up, and maybe I can actually make it a little bit more extreme. Let's see, damping. Is this the one? Or I can make it a little faster. So what you can see what happens. People get stuck in the mud. So there are more people on the left side than on the right, right? Because they get stuck here. Yeah. And so the center of mass is, so there's a momentum. That means what happens is you get a momentum vector that's moving to the left. Yeah. Yes. And you can even get, let's see this one. You can even get gradient index. Well, you can even get it to bounce back and forth. So let me just increase the time scale so it's going a little faster. So it will overshoot a little bit, right? And then, of course, the people on the right are more stuck in the mud, and it will go back and forth.
Oh, I see. Yeah.
So this is, and then
that's I like it. That's really great. I love it.
We could actually something you could actually try. You could take a class, elementary school class, and try that to see if that's actually, if that's how it works. But yeah, hopefully this is a bit more clear.
Yeah.
So now we can do this also with sort of a wave representation. So imagine this is some kind of standing wave, right? And you can also see that this is a gradient here. We have a gradient, so a refractive index gradient. And for one thing, also the clock speed is different, right? Where you have a higher refractive index, the clocks will move more slowly than on the other side.
Yeah.
And this is a little bit slow, but again, you get this momentum vector, and the wave will start to move towards the higher refractive index. And I'll share all these links so people can play around with this. So I don't want to spend too much time on that, but hopefully this explains this a little better. And I know, obviously there are people who say, well, wait, there can't be a medium, because the speed of light is constant for all observers also. Because now what I'm saying, if people paid attention, right, we are saying the speed is constant for the particular stiffness and density, right? Relative to the medium. The wave is you always look at what's the speed of the wave relative to the medium and not relative to each other.
That's a really good point. Not relative to each other. Relative to the medium. Yeah.
So far, that's all I've been saying. And this sounds like a contradiction. It sounds like, hey, you are actually contradicting standard physics. It sounds like it, but you will see it will all cancel out. It will actually you will get special relativity out of it, which is interesting. So anyone who complains about this, they should really think it through step by step. And if I make a mistake, you let me know. But and also there's papers about this as well. This is not based on my own paper. This is based on Robert Close has written a paper on this. If you want all the math, is in his paper, and I'm gonna also share the link. So that's one criticism, but we will see it all works out. There's no contradiction at the end. It's only philosophical. And then the other thing that people complain about, if there's a medium, there's a preferred frame. Well, it depends what you mean with preferred frame. Yeah, sure, there's a special frame, like the rest frame. But the thing is, it's not preferred in the sense of that the laws of physics are different. The laws of physics are the same in every frame. In physics, I can pick any frame I want, right? There's no reason I can't pick that frame that's the rest frame. Why shouldn't I? I can pick any frame I want. So it's not, it depends what you mean with prefer, right? It doesn't change
You could say every frame is preferred. Like every frame is special.
I can pick
every
frame
is
want,
special.
Right? There's no reason. Yeah, so...
Yeah.
There's no contradiction. It's just, I don't know, for some people maybe they read it somewhere and they think this is a contradiction.
They're just perpetuating it. They heard it and they're just saying it. Yeah.
So let's start with the clocks, right? So in special relativity, moving clocks tick more slowly. And I'm saying it on purpose that way. It's not that time is slower, because in this model, right, where there's a medium, time is not really changed. I don't even know what time is. Time is some, the change over time. It's basically
change.
Changes.
It's just change. It's an emergent property of change.
Yeah, exactly. And the thing that is changing is this speed of the clock ticking, really. That's the thing.
So a lot of people refer to this as clock retardation. So a lot, like there's actually a term called clock retardation, which is clock slowing down. I guess people don't want to use that word retardation because it's got other context, but
yeah, that sounds kind of weird. Yeah.
But there are a few people I've seen use that term.
So I made another person. I like these people demos because I think these are really easy to understand. So here is an example, right? So we have Bob on the left. This is a Bob clock. When Bob always runs at the same speed, like 10 kilometers an hour, and he runs back and forth. And when he's done one full round, that's one tick.
Yeah.
Or is it two ticks? Either way, it's a tick. This is our clock. We don't have any other clock. That's all the clock we have in our world. And so the other Bob ran away. So now this is stationary clock, right? And now, of course, when we have, now we are kind of mean. We are actually moving. Oh, this is a bug. So basically the plates should be moving, but not, of course, the floor, right? Anyway, so I just noticed that now. So imagine only these plates are moving, not the floor here. He's still running on the same floor. Oh, no, I missed that one. Now he's still moving at 10 kilometers an hour. Of course, he has a longer path now, right? He has a longer path.
In this visualization, you have him sort of pointing sideways instead of you would get the same, right? So you want him to think, you want to visualize it so he's running the same. He thinks he's running, back and forth, and he's not. The other guy's pointing sideways. So that's kind of
the next slide. I do have that one. So I think this part is clear, right? Like, if imagine this is not there. This brown board is not there. He's actually running on the regular floor, right? It's just the panel that's moving. So this is a mistake. I'm gonna fix it before I share the links. His path is longer, so it's gonna take him longer to complete that one cycle, right? So I think that part is clear. And I know exactly what you're saying. People have been complaining. Well, wait a minute. Well, how does Bob know? Or a light wave or a light beam that it's gonna change the angle, right? So here's the same simulation, but instead of with Bob, we have it with light. Okay, so this one is maybe a little bit better. So again, you have the stationary light clock. So when it's up and down, it's on tick, and then the moving one, you can see the path is longer. So obviously, it's ticking more slowly because the speed of the light wave is relative to the medium. Okay.
Yeah.
But then the complaint was, well, now you draw this angle. Like, how does it know, right? Well, yeah. But the thing is, in real life, of course, where's the wave? Did I actually the wave? Oh, there. This is the wrong. Oh, I see. I have it in the image, but I think I don't see the button here to moving only, stationary front, circular. Oh, I have the circular wave. That's another one. Anyway, the light wave is really something that it spreads in all directions. I need to show it on the slide, right? So I didn't update. Yeah, I wrote the code, but I somehow the link is not. Maybe I didn't save it. So you can see that the light wave is emitted. It's a wavefront, right? That's going in all directions.
Yeah.
Just because we like to draw it that way doesn't mean there's a light beam like this, right?
So that answers the question I was going to ask. So that's good.
Yeah. So then, of course, in this case, it would just take another place here on the circular wavefront, right? Would hit the panel here, right? So now the question is, of course, well, how much slower is that clock? And this is really a simple Pythagorean theorem. That's really all we need for this is this. So here is the same thing again. It's just that we have the stationary clock here, right? So we have the length of this we call it L for length. Let me just maybe restart it. So the stationary clock, we can calculate how long it takes. So, the time is the length divided by the speed. So T0 is L divided by C, right? And then for the moving clock, well, the moving clock has a longer path. This L is still the same L, right? But now the path here that the light beam has to take is now C times, because C is the speed of the light, times whatever time T we don't know, whatever time it is, right? We don't know what T is. It's taking it's a little longer. Well, how much longer is it? We can calculate this by constructing a simple I cannot say this word, Pythagorean triangle. So here we have one side is vt. V is the speed of that, how fast that L or how this clock is moving. That's V. T is whatever time that we want to calculate is. L is still the same. So we have, ct squared is equal to L squared plus vt squared, right? That's this one here. Let me see, I'm moving over a little bit. And we can calculate, you can check it, it's correct. So you can take this one to the other side, you can factor out the t squared, then you divide by c, take the square root, and then you get t is equal L over c times the square root of this, right? And from on this side, remember we had t0, that's the normal, the stationary clock speed is L over c. We can just replace this part here with the t0, put this in here. We can also, some people use, beta. Beta is defined as the ratio of the velocity divided by c. And then gamma is written like this. And you get that formula, right?
So you get the Lorentz
that's
contraction or expansion from just pure geometry.
Pure geometry. And the only assumption we made is there's a medium. Speed of light is constant in that relative to that medium. That's all we did. So literally, that's pretty simple, right?
That is very clear. That is the clearest explanation. You did a very good job.
Okay, good. I'm glad you're telling me if I'm, going off the rails or something.
I don't know about anyone else, but I think I understand it even better than I did before. So
good. Because once you see it, you cannot unsee it.
Exactly.
That part is obvious. Now, of course, length contraction is a little harder to explain. So, and I know this is a bit tricky, so I'm going to try it in a different way this time. I like my people, this demo, so let's try that, starting with this. So imagine, the grass is our medium, and the people here are light waves, the crests of the wave, for instance. And like imagine.
So this is like the cars in the clowns in the car, where the car is full of clowns and they keep coming out. No, sorry.
Yeah. So they come out at the same time.
Yeah.
Come out front and back. So they have military precision. They always walk at the same speed, 4 kilometers an hour. That's it. The speed of light. That's the speed of light. The speed of these people is the speed of light, right? In our analogy. Yep. So far, nothing really interesting. But now what happens when we move that truck? So let's start to move the truck a little bit to the right, okay? Well, obviously, as the people come out, the truck is catching up with the people. So you can see there's a contraction here, right? The people are now closer together on the front side and further apart on the back side. They're still moving at the same speed. They're still 4 kilometers an hour. But now they're contracted. So that's basically an explanation of the Doppler effect, right?
Yeah.
So
that's the Doppler effect.
Well, yes. And we can
Which is obvious, yeah.
Yeah, let me also, this is a little more one step further using, this is now a truck where people come out on all the sides, right? So we can see like the wave, in a way, the wave front, right? So the people that come out at the same time, this is one wave front. And now the truck starts to move. And look, it's just Doppler effect, right? So you can actually do the Doppler effect with people.
I love the animation. That's fantastic.
That's funny, right?
It's funny and it's very visually.
Right. So just keep in mind the people, they always have the same speed relative to the grass. That's it. They cannot move any faster. They're told 4 kilometers an hour, and that's it.
The speed of people. Yeah.
The speed of people. And you can even get, I guess, I didn't go all the way to, so the speed, C here is 4 kilometers. Like if you went to the speed of the people, then you would get like the sonic boom, right? You would have a sonic boom because all the people would accumulate there in front.
Oh, yeah.
I should do that. I should let it go all the way to C.
Because in sound, like you can go faster than the speed of sound, and there is a sonic boom. Yeah. So this could be applied to any medium.
Yeah,
right?
yeah, exactly. Yes. So hopefully this is clear. Doppler effect, why there's a compression on one side and why on the other side there's the distance is further apart.
Yeah.
Okay, now of course we can draw the same thing. Like with a sort of, instead of people, and that's I think what I started last time, probably using a wave representation. So this one here is the stationary truck, right? people coming out. So this would be like a person here, a person here, a person here, basically.
Okay. Sure.
And this would be the moving truck. It's just in this case, we followed with the camera. So you can see the compression in front. And there is one difference that I didn't mention. And some people thought I missed it. Maybe I did miss it last time. It's possible. Because guess what? The moving truck, it's now a moving clock, right? In this case, I don't know if you can see the stars. There's supposed to be stars that move past this. But anyway, the moving truck, there's stars. See, there are little dots here. So it's moving. This moving truck, of course, is not ticking as fast anymore as the stationary clock because we have time dilation. So that's another effect, because if you didn't have that, I think it's mode A, you would get more, the Doppler effect wouldn't be quite right. You would actually, if you calculate the formula, you would get difference to special relativity, because we have to consider that as well. It's not just that we have the Doppler effect, it's also that the moving clock is ticking more slowly. You have to consider that as well, always, right? All these like experiments, you always have to consider both, right?
Yeah, you can't decouple them.
Yeah, no. Because if you forget one of them, the math will not work out. So yeah. And so let's see. And then, so here is another example. Oh, here's the math. Okay, here I have the demo with the math. I think maybe last time I just did that one alone, and maybe that was a bit too much. Can I slow it down a little bit? Oh, that's way too fast. Let's see, frequency. Oh, I can slow it down. Okay, so here is just, again, the same thing, but now a little bit abstracted. We have this source that's emitting waves, right? And now we can start to move the source. And now we can see, well, when we have a stationary detector, we can, each time it blinks, it's receiving a signal, right? It's the same thing, right? Because now, because when you look at how quickly, because the Doppler effect, right, it's more clear when you speed it up.
So it's blinking faster as it gets closer, and then now it's blinking slower. Yeah, that's how I always visualize it in my head.
Yes. Yeah. So when the detector, when the source is moving towards the detector, the frequency would be blue shifted, right? Because if it's stationary, you have a certain frequency, right? But then, because of what we just saw before, the people coming out here, basically, they're closer together, right? So maybe we can increase the frequency a little bit. They're moving closer, they're closer together, and so the detector would observe, the beep more often, which is
exactly
frequency, which is the blue shift, and we can also go the other way, and then the other way would be then the red shift, right? So now the
so that's just the Doppler effect.
That's just Doppler effect. We can do the same thing. We have a moving source. We can also have a moving detector,
and it's moving at a constant rate.
Yes, right now we all very simple. Now we can also move. We can keep the source stationary and move the detector. It's the same thing. It's the same math. And if you want to look at the details here, like you can. It's the calculation is very simple. Then I'm gonna not go walk through all the details because it will take too long. But I think it's very simple because
I can see it. Yeah.
Plus, this is speed of the wave plus the velocity of either source or detector, and then you can start to calculate. The shift, the blue or red shift, right? Now, of course, both can be moving too, and it's just, it just combined the two effects, right? And when you do this, the algebraic steps overall, you get the standard calculation for the Doppler effect, right? Now, the thing is, people will say, wait a minute, for sound, isn't it slightly different than for light? Yes, because here we are not considering, if you look at sound, the clock is not changing the speed because we are using our clocks, right? We're not using a sound clock. If we were using a sonar clock, then it would special relativity. But normally we have our normal watches where we measure these things. So in the case of sound, we are not considering time dilation, even though there would be a tiny one, but you wouldn't see the difference. You wouldn't see the difference because the speed of sound is very slow.
But if you used a sound clock, you would.
Yes, and for light, we also have to consider that the moving clock is ticking more slowly, and so that's why overall we get actually, instead of the formula we had before, we get a square root of this, and that's the difference. So there was some comment saying, I think I probably didn't mention it last time, because that's easily missed, right? When you have measure for sound in air, you don't need the time. You don't have to consider the time dilation. It's too tiny. So, but for light, using our light clocks, whatever, then it matters. And so you have to consider that the moving clock is ticking more.
I think that's a really important point. I'm glad you made that. That should clear things up for a lot of people
hopefully,
that are trying
yes.
to apply this to, sound medium. Yeah.
Yes. Yeah, well, people will say, well, but you're using light clocks. But actually, our clocks are not all light clocks. But the thing is, even an atom, when you even have a normal ticking mechanical clock, when you zoom in, or one of those, just any clock, really, deep down, it's atoms, and atoms, they are composed of wave functions, and they're waves. So it is still waves at the end when you zoom deep down into it, even when you have a mechanical clock. That's, yeah. So the next thing is length contraction. And for length contraction, let's go back to the trucks. Let's see if I can explain this better this time. It's a bit tricky to understand maybe initially, but so let's just start with the stationary. So now we have these two trucks this time. And they're emitting bobs at the same rate again, right? Like before. So in the first truck, they go to the right, and the one truck on the bottom, they go to the left. And they're stationary, right? And this is to represent an object, like let's say a rod. Okay, this is our measuring stick, for instance. We have composed of people waves. So these are wave crests here, right? So yeah. So what happens? What happens when the measuring stick is moving to the right? And so let's see if the bottom here is following this whole scene. You can see what happens, just like before, the Doppler effect, that the people on top, because the truck is moving with the direction of the people, they're closer together as they exit the car, right? So you have the Doppler effect, right? And at the bottom, it's the opposite. The people walking to the left, they are further apart, right? Again, this is Doppler effect. So, well, how do we now calculate the length of this stick? We have to combine the two effects into one. Let's see. And it's probably better when I show this with, I do have waves. Oh, I do have the waves. I don't know. I have another visualization right after. So here, the top wave here is you can see each crest is a person. They're closer together, right? So we can, so do this. So stationary, this would be the stationary situation. And you can see the waves are the same, top and bottom. But now when we start to move them more and more quickly, the wave crests, they come much closer together, and at the bottom they're elongated. Okay. And so we have to, because when we deal with the waves in a matter wave, right, we have to add up all the waves together. All the waves add up, and when you add up all the waves, you get a shortened wave. It's just simply when you add them all up, that's what happens.
Okay, so I'm not clear on what the middle sticks are. Like, what are...
I don't think they're necessary. Well, I should probably remove them. Initially, the idea was to have sort of the yardsticks, the distance between the people, but I think it's, when it's stationary, it helps. Like,
it's a little tricky. I think I get it, but I just want to make sure everyone is clear on it.
Yeah. But hopefully it's clear that...
So this is an extra contraction that's outside of the Doppler effect.
It's still the same. It's the Doppler effect. Ultimately, it's related to the Doppler effect, right? But in a matter wave, we don't just have a light beam. In a light beam, we have only just the one beam. But in a matter wave, you can imagine you had a wave going in circles, for instance. I do have this demo here. Let's see if that helps. So imagine, again, we are looking at people walking in grass in a circle, just like before. In this case, we don't have mud. It's just grass, okay? They're just walking in a circle. And now we are telling them, hey, guys, move the whole shape to the right. Move your whole circle. But the thing is, they can only walk at 4 kilometers an hour, right? Relative to the grass. They cannot move any faster. That's it. They have their speed they cannot walk faster. That's just, right? They cannot do it. Otherwise they will exhaust. now we're doing is wrong. Now, on the left side, they're still walking the same as before. Now, on the right side, I'm showing how it's not correct. If we keep that shape of the circle the way it was, you can see now the flowers here, right? Move to the left. So they're moving relative to the grass. Well, what happens to these people here? They're now moving faster than 4 kilometers an hour, right? And these people here are moving slower than 4 kilometers an hour. Well, that's not what happens. The speed of light is always the same. And these people are always walking 4 kilometers an hour relative to the grass. So what happens is based on the speed, they're gonna slow down, right? They're gonna bunch up. They can't. That's a Doppler effect, right? On this side, they're gonna bunch up.
Yeah.
And on this side, they're gonna have an increased distance. So you cannot keep the circular shape. It will contract. And I'm sure, I don't know, maybe people should try this with some school class or something. It would be interesting to see if that's what happens. Of course, you would have to make sure you keep, maybe with robots, I don't know.
The robot could do it.
Roombas or I don't know, Roombas.
Well, you'll have to change the people to robots for the next animation, next video.
Because they're always walking at the same speed.
Yeah.
You know what I mean? Yeah. So hopefully this is a bit more understandable why you cannot keep the circular shape. It's not possible, right? If you did, it's not possible. They would be walking too fast. You cannot go faster than the speed of light, right?
Yep.
You see that? Yeah. Okay. And this is the same thing, really, just shown in a slightly different way with these clocks. Again, we have the stationary version here, and we have the moving version, right? So for the moving version here, again, we have the going to the right, it's more compacted, and going to the left, it's elongated. And the thing is, when we add up those two waves, when we add up this forward going and the backward wave together, we get this wave shape here when you add up. If you just literally, of course, I would have to draw it all the way to the right. You have to imagine you're overlapping them, right? You're overlapping them.
Sure.
So this is what it will look like. It will contract. And again, this is missing the time dilation thing. So in reality, when we talk about special relativity, the moving clock is ticking more slowly. So now here, I wasn't including that. See, they're ticking the same speed. Of course, when they're moving, the white one is moving more, it's ticking more slowly. So the contraction is not as much. You see, it's actually a little less when you do that. You can see the difference. So this is without time dilation. This is with time dilation, and then you get the correct result. Because if you forget,
that's what we're saying. We need both.
We need both. Yes, we need both, and then it's correct. Because some people commented, "Hey, it's actually not correct. You're missing some square root, or I don't know exactly." But So that's the thing. I don't know if you want to go through the whole math, but if anyone wants to, I'm going to share the link. But here, I don't think
you're going to share the link to your presentation.
If anyone has a question,
Perfect.
I mean, because
truthfully, it's kind of small. It's hard to see. Very tiny. Even with my glasses on, I can't really see.
But all the steps are here. This is from the Doppler effect we talked about. It's the same formula we talked about. And then he's just putting things together, and then you can see that you actually get the correct get the correct length contraction, and you can check the formulas, and there's so buttons. So I'm not going to spend time on that. It's not that interesting.
So definitely, people should check out that slide.
If you want, people who don't want, if it's just for understanding, I think it's probably sufficient. But some people like the math, but I don't want to spend too much time. To me, that's not the fun part. So
no, it's too hard to see on the screen. Anyways, the numbers are too small. So it wouldn't do it justice.
Yes. And no, here it's just because now before we had a simple wave, right? It was just a sine wave. That's obviously not matter. It's not going to be like that. A matter is something that the wave is more complicated. It's not just maybe some I have this complex wave shape here, right?
Yeah.
And so it's the same thing, really. So basically, we have a forward going wave, this blue one. We have the backwards going wave, and together they create this complicated wave shape. This is the amplitude squared, which corresponds to the probability of detection. And when you add up those two waves, it's just added up. You get this. You get the same wave shape, but it's contracted.
I see.
Again, you can do this for any kind of wave shape you want, which is nice, right? So it doesn't really matter it's not just for sine waves. It's, you can have much,
and it's contracting in the direction of motion. It's not contracting like symmetrically
Not
in all
side. Oh, by the
directions.
way, not sideways, right? Yeah. So some people might ask, well, let's say you have a square, right, moving.
Yeah.
It's only contracting in the
Yeah.
direction of movement, not
Yeah.
sideways.
The
So
amplitude
sideways
doesn't
not
change. Yeah.
affected. No, sideways not
Yeah.
be affected.
Yeah. Just to clear that
Yeah,
up.
exactly. And so yeah, I think that I don't need to show this again. But the funny thing, I just thought was kind of funny because the way a meter is defined is kind of weird because it's actually defined as the length of the path traveled by light in vacuum, which seems kind of circular, right? I mean, it's kind of crazy because when you look up what in Wikipedia, whatever, what the definition is of length, that's what it is.
Yeah.
Which is weird. Like it's circular. Of course, it works out because this is how special relativity works. But if you were just like, let's say you didn't know about special relativity, right? And you wanted to figure out how it works. It's really strange to define the length that way, right? I mean, why would anyone do that? This is only after special relativity. Yeah, that only makes sense. But if you're trying to define, actually derive it, it seems kind of circular to me.
Well, I think it's kind of, to me, it feels like a calibration issue. So the way I understand it, so they calibrated the second, just fairly recently, actually, and like not that long ago, to be exactly 299,792,458 meters, or sorry, yeah, so meters per second. So they calibrated the cesium atom to make sure that that number was exact.
Yeah.
Before it used to have a decimal place. So it's kind of a calibration issue. And then the distance light travels in, a certain amount of time is the meter in that amount of time, whatever the cesium clock is. So they calibrate the second to the cesium clock, and then they calibrate the meter to the speed of light.
Yeah, it kind of does. Like once when you consider there's a medium and consider that matter is composed of actual waves, then it kind of makes sense. But if you're thinking that, like standard physics, there's first of all no medium, and then matter is like point particles, like isn't that weird?
No. This is almost a proof that matter is a wave. That the fact that this works, right?
Yeah, it's not a proof. It's just saying it's
consistent. It's a proof.
I wouldn't go as far. I can't prove anything really.
No. I'm just a proof in like it's maybe the proof is the wrong word. It is
it's an explanation, and so
explanation.
This way we get an explanation that makes sense, a mechanical explanation. And in standard physics, there's none. It's just an assumption. Speed of light is constant. That's it. We don't know why. There's no reason. It's just
no.
That's what bothers me. It's not wrong. It's just the explanation makes no sense. And
and the fact that waves are constant in every other medium that we ever tested, it seems silly that we then say, oh, but this is different.
I know, right? So to me, this actually makes sense now because if matter is waves and not particles, then that actually makes sense. Otherwise, it's just totally crazy, right? To me, it's like it's totally fantasy or something. I don't know. So now we have talked about this before, Michael Morley, but I just want to bring it up again because people keep saying, hey, there was this experiment, and it was proven all wrong and all that stuff. And the main issue was that there were some assumptions made when they did this experiment, right? They didn't consider length contraction. So I don't know if you remember from last time when we talked about this. So have this Michelson-Morley experiment again. So right now we are stationary, right? We are sending out a light source, and I'm on purpose using particles here just because we can see, this one is the green one. They match up, right? So the colors match up. So they're overlapping exactly. When they're overlapping exactly, there's no interference pattern, right? Yeah. So when we don't use length contraction, when we use, like they didn't think of it. I don't know if they didn't think of this, or of course, if you think the whole contraption is, I don't know what they were thinking. I guess they forgot about it.
Did Lorentz come up with length contraction after the Michelson-Morley experiment?
I don't remember the dates. In this experiment, they forgot to consider it somehow. I don't know. Maybe it was before. I don't know why. Of course, and then if you have this whole apparatus moving, and if you keep everything fixed the same length, and if you want to, so the test here is, right, you want to test if there's a medium. And so, of course, going forward, light would slow down, right? Because it's going against the medium, speed. You can see the little stars here. And when it's going backward, it's going faster. Well, in that case, the colors, they won't match up. The light waves won't match up, and you get an interference pattern, and you could detect that, right? That's the whole idea of Michelson-Morley experiment. And, it gets worse as you, well, of course, at some point they will overlap again. But the thing is, they did not consider length contraction. And of course, you have to consider that,
Yes.
Because when you move it faster, the whole, I'm going like 0.95 speed of light, it contracts. Let me just speed it up a little bit. Wave speed, let's just make it faster. So otherwise it will take forever. Then it all cancels out. So, which sounds like a conspiracy, but when you do the math, it all cancels out. Sure, the forward going wave will be really slow, as you can see here. And when it goes back, it will be super fast because you can see the sideways again is not affected. The sideways speed is the same, but it cancels out. So the length contraction and the change of the relative speed for the single one-way speed of light, right? It cancels out, unfortunately. So we cannot detect it, which is a real bummer.
So there can be an ether. If they had taken length contraction into consideration, they could say, well, there still can be an ether.
Yeah.
Not that there is an ether. No one maybe can prove that there's an ether, but you could still say, yeah, there can be an ether if you take length contraction into consideration.
Well, we have to, right? Because if everything's based on waves, maybe the reason is they didn't consider the apparatus as waves, right? If they thought light is only wave, but the apparatus is
that's exactly
particles, then they might think, well, there's no length. Why should there be length contraction, right? If everything's particles. So maybe that's why I don't know the reasoning.
Length contraction was eventually implemented, though, in relativity, and so to fix the problem, obviously.
But they forgot to update the experiment. They forgot to, maybe re-evaluate the former experiments. People just
but like when they talk about the experiment, they do say, oh, length contraction. They do talk about length contraction, I think, in the context of this experiment.
I don't think so.
No? But they never went back to saying, well, that there could still be an ether. That doesn't, the fact that there's length contraction means that there could still be an ether instead of saying, oh, there's no ether.
Yeah, some people know, like some people realize, with the length contraction is consistent with an ether. Yeah. But a lot of people, like in the comments, sometimes they will just say, oh, Michael Morley has proven this wrong. Like
I know, I get that all the time. Yeah.
Without thinking about it, you have to actually. I feel like we should reread a lot of these older experiments with updated knowledge that we have.
Yeah.
Because maybe there are other wrong conclusions. There are all these conclusions we just take forward. And then we learn something like length contraction, and then we should re-evaluate some of these older
experiments with
that in mind. Like we know something, we know about matter waves now, and same with the photoelectric effect and all these things we'll talk about later. Yeah, so maybe we would come to different conclusions. Kind of what James is trying to do, right? He's trying to go over everything again.
Yeah.
So now, great. Of course, there are people hoping, well, maybe there's still a way to detect the ether. And I get lots of emails with people with ideas. Hey, could we do this experiment to detect it? I know how to detect it. I even thought I could detect it multiple times, by the way. So now I know better. This is probably a Dunning-Kruger effect. Like you think and suddenly, oh no, I forgot time dilation, or I forgot whatever, the clock synchronization. That's the other thing.
You have to rethink everything you think over and over and over again.
A lot of details.
I do that. Yeah.
So
I don't assume I know something.
Yeah, there's a lot of this has been inspired by Robert Close, and I encourage people to read his papers because he's very mathematical. He goes right into the math, but he also has some simulations kind of like this. So underwater relativity. So he's explaining this with underwater submarines. But then the submarines have is also a sound clock, right? So here the question is really. And of course, here I'm also considering length contraction, because if we didn't use length contraction, so here, if I'm not using, this is stationary, and here's the moving, right? We have to consider length contraction or we do not get the correct result. The question is, well, can we just find out somehow that the submarine contracted, right, by measuring it? Of course, we cannot. And again, I'm not going to go through all the math, but it's the same thing again, if this is our clock here, so one's up and down, that's our clock, right? We call it one click.
Yeah.
And the moving clock, of course, moves. It's more is slowed down because it has to travel a longer distance. And again, it's the same math again as we had before. Now, when we measure the length of this, so this is the top shows the clock, right?
Yeah.
Again, like before. The bottom shows how we can measure the length. And how do we measure the length? Well, we have this beam, this sound beam in this case, or a light beam, right? And we check how long it takes. It bounces off, it goes to the front, and it goes to the back. And then we just check how long it took, right? Mm-hmm. In this case, it took one click. Was it one click? Yeah, of course, I chose the length, so it's just like one click, basically, right? That's the thing is, you would think, well, in the moving case, it will take a lot longer going forward, but then it will be a lot faster going backwards. Unfortunately, because the clock is ticking more slowly, it all cancels out again. You get the exact same answer. It's really unfortunate. But once you see that, it will dawn in people's mind that there's no experiment we can do, nothing like this that will allow us to measure that ether, unfortunately. And I know even still the people send me stuff, like the twin paradox also. Let's see, should we do that one? I don't know. Let's see. The twin paradox is, the question there is why? Okay. So we have this twin, right? These two are twins, twin A and B. They're the same age when one goes away. The twin B flies off to some buoy. I specifically did not take a planet because otherwise there would be gravitational changes. So it's just some marker. It's going back and forth, right? And clearly, well, twin B moved more than twin A, right? And we can calculate, based on special relativity, we calculate the relative, and we know the relative speed they had relative to each other. And then we see a time difference here. So we see this twin aged 12 time units, and this other twin, when we look at this, aged 10 time units, right? You might think, well, what about when we change, what if happens if we change the situation? So now we're moving this whole scenario here, right? So now we're moving everything to the right. So the whole scenario is moving to the right relative to the ether, right?
Okay.
Interestingly, we get the same result because, again, times, both clocks are slowed down because of the relative motion towards the ether. And this one is even slowed down further, going one way because it's faster, and then slower on the other. And when you do the math again, it all cancels out, unfortunately.
So they don't age more.
Yes, but always it's always the same. It's like you can always tell which one. It's always
I see.
The same. Like
it looks like the same. Okay.
The official, I think I've seen, because
I get it. Yeah.
Theory, right?
I couldn't see the number. So the top is still 12 and the bottom is still 10, regardless of whether the whole thing is moving
and the reason, the official reason you would often read is that, well, the twin B had acceleration when it turned around, so that's why we can tell which one actually moved. But because the idea is, well, what if we didn't know which one moved? Right? We have two twins. One moves, the other one doesn't. Because of relativity, we should be able to pick anyone at rest. We should say, well, maybe B was at rest, right? We should be able to do that. We can pick any frame. What if I pick twin B as rest frame, right?
Yeah.
Why is the result like this? It's still always the second one that ages less, right? Why?
Yeah.
Well, in this case, when we have, of course, an ether, it's easy to see because you can always calculate it relative to ether. But in standard physics, there's no ether, right? So how do they explain it? And the explanation is kind of wishy-washy, it seems to me. They say, well, because twin B had experienced acceleration, so we know which one moved, right?
Right.
It seems kind of like a fishy thing, but with the ether, it's clear. There's no question. You can just do the math relative to the ether, and there's no mystery actually at all. Even if you reverse the scenario, you can do the math. You always get the same result because overall, twin B moved more because even it's going back and forth, it moved more, right? Relative to the ether, doesn't matter how you look at it.
Yeah. So the paradox is always like,
it's not really a paradox.
But the paradox in people's minds are, because, I see him moving, he sees me moving, right? So there's this sort of, I don't know who's moving. I don't know, when not from relative to me, the other guy's moving, but relative to the other guy's moving. but only one person is actually moving.
The thing is, because how do you measure the time difference? Well, they have to come back, right? That's the thing.
Exactly.
That's the thing. And so, of course, people come up with other experiments saying, well, maybe we can trick the system. We're not including any acceleration anywhere. Let's see. But to explain that, we need to explain the clock synchronization issue. So that's this thing. The thing is, a lot of people think about that and they say, hey, I have an idea. We just have no acceleration. We just measure, the twin peak only goes to the buoy. I don't know how to pronounce this word. You detect the time and then you take the clock back and compare. But the thing is, so these clocks here are all synchronized right now. Right. But the thing is, as soon as I move one of the clocks, now the light path is longer, right? When I move it, now it's slowing down and now they're no longer synchronized. The tiniest movement will cause this, right? So unfortunately, you can never keep them synchronized, no matter how hard you try, whether you move them fast or slow, it will not work. You will not have them synchronized ever.
Yeah.
And the thing is, since we don't know where the ether is, we cannot calculate how much it would slow down, right?
Uh-huh.
Like we don't know where the ether is. We don't know if we knew what the rest frame was, we could, of course, calculate. Well, we know how fast it's moving, right? Yeah. So anyway, we cannot synchronize clocks ever, unfortunately. So let's see. We could think of another experiment that is more clever. Now, I'm not sure if I want to go into all details. This one I hope it's the right one. Yeah, that could be it. Yeah, I think that one might be. Okay, so I'm going to start this one. Okay. So we have two spaceships. Okay, now we're going to be clever. The thing is, we want to be clever. And just look at the left side. We're not going to use acceleration, because that's often the way you can tell which one moved faster than the other, right? So all we're doing is we agree up front, okay? I'm going to send out 5 light beams. Okay. And that's it. And then as soon as the red one measures, gets the first wave, my clock is ticking, right? 1, 2, 3, 4, 5, and then we stop. So after 5 light beams, we are stopping the experiment, and I'm just checking how long it took, right? And in this case, the blue one is moving, and the red one is stationary. And we are checking how long it took. And the blue one, of course, is also measuring how long it took it to emit those 5 light beams, right? It knows, like, I'm starting now, 1, 2, 3, 4, 5. And we are comparing it. And then we're on the right side, we're doing the same experiment, but now the red one is emitting the light beam, right? And the blue one is detecting it. And we are trying to trick the system to see if we can tell which one actually moved relative to the ether, right? We're trying to be smart, because now there's no acceleration, right? There is no acceleration anywhere.
That's a good experiment. Yeah.
There's no gravity. There's no clock synchronization either, right? Because all we agree, we're just measuring how long it took from the first light beam to reach.
So you don't send the beams out until the moving one, the blue one, is at going constant velocity. So you don't even start sending pulses. You're removing the acceleration. Yeah.
Yes, that's all we're doing. So there's no acceleration, no gravity issues, nothing like that. No clock synchronization. We're just sending out those 5 and measuring how long it took. And you can see it's different, right? Like here, it's done already, and here it's taking much longer. Right?
Yeah.
Not even done yet. Now, the thing is, again, as it's not unexpected, is when you do the math again, overall, you get the exact same results. Unfortunately, because of the time dilation and all that, right? Because the moving one is emitting the light beams more slowly, and its clock is ticking more slowly, and so on. And because of the Doppler effect, the waves are spread more apart. And so, unfortunately, you get exactly the same thing. You cannot tell. Basically, you cannot tell which one is faster. You get the same. Here it results. Yeah, you get the same results overall. When you look at, I'm not going to go through all the numbers, but I'm going to show you.
I expected that, but yeah, this is a good way to visualize it.
So this was actually an idea was it James Blackmon? I think he sent me the idea. He said, "Hey, Chantal, God, I can detect the ether." He wanted to write a paper about it. And for a moment, I was actually convinced. I thought, that, oh my God, this is genius. No acceleration. Yes, let's do it. And I actually, when I wrote the code, that was before AI, by the way. So I tried to show that there's a difference. And guess what? There was none. I'm like, oh no, is this possible? Until I got it. And I, of course, when you consider everything, time dilation, everything, Doppler effect, you cannot detect it, unfortunately. Anyway, so I pretty much given up. I don't think that's the way to go. We cannot detect the ether in any such regular experiment.
And I think it's actually a good thing. Like there's an independent researcher called Robert Distinti. I don't know if you ever heard of him, but he calls this the gift. He calls it the gift because I can be in a train moving and I can throw a ball up and catch it. And it's the same as if I was not in the train and throw the ball up and catch it. It's, you know what I mean? Like you don't want the moving thing to behave physically, the physics to behave differently inside the moving thing.
Awesome. Yeah.
As if you're not moving. And so this is actually a good thing that, you get the same answer, in my opinion. It's a gift. It's the universe's gift so that, your reference frame is your physics is going to work and someone else's reference frame, the physics is going to work.
Right.
Yeah, it's a good thing.
Another one, of course, is other people will say, hey, I know, aberration. So let's look at that one. You would think that, let's say we have some kind of beam that, some source that's emitting light beams and a detector here, right? That's all you're doing. And now we're moving this thing and we think, well, if we remove this, then there will be a shift, right? Because now as the light is being emitted, the detector will be moving and then it wouldn't be at the center anymore, right? That's what we might be thinking. Unfortunately, that's not the case. It will still be at the center because, again, the light, it's not a beam. People think the beam will go straight up, but that's not the way it works. It's a light.
That's the mistake I was making too. Yes. I made the same mistake in my head when I was doing the thought experiment, this exact kind of thought experiment. I was forgetting that is a sphere, it spreads out as a sphere and not as a
Interesting
beam.
Again, if light were particles, then how would you explain that? Like, because light is a wave and it's actually a wave front that's being emitted.
Yeah, it's a wave front, yeah.
We can also follow it. That's why there's a whole, like we could actually draw a whole circle, right? Because I was just drawing a slice. It's a whole circle normally, unless you block it on one end or something like that. But if it were particles, like everyone who feels like light is made of particles, then that doesn't make sense. Well,
and that's how they always visualize it, the way you did just with the sphere, like the photon. It is confusing, and this is not confusing when you model it as a wavefront, a spherical wavefront.
Yeah.
And I can see why you made those little people face sideways, right? Because I thought, oh, why is she making them face sideways? Well, like the beam is kind of coming in from the side. So it's actually
of course, but the people, they're like, what you should do with the people is have a whole front of people marked.
Exactly. Yeah.
Like a whole,
and then you would see
bobs up and down. And then when all of the bobs, when it goes sideways, then you will see that it's not going to be the same bob hitting the wall.
Exactly.
Yeah, that's actually, maybe I should do that to make it. That
would be cool.
That would be nice.
Because that would sort of visually explain why you made the guy, face sideways instead of straight.
Or robots, a bunch of
robots. Robots will be cool. Do robots next.
A front of bobs. Yeah. Okay. So that won't work either, unfortunately. So, and unfortunately, there's another one. The one-way speed of light. So this is a big, people often say, oh, this is a conspiracy. People, if they were just to measure this one-way speed of light, we would finally know that, the speed of light is not constant, right? And so let me just, this is a bit too fast. Let's see if you can slow it down a little bit. Let me just reset. So imagine we are trying to measure the one-way speed of light, okay? Here's the start, here's the end, and we want to put a clock here, right? So we can see we are sending a light beam one way, and we see how long it takes. And then we are sending this light beam back the other way, and we check how long it takes. And then, of course, we know, like if there's an ether, okay, we know that if this whole thing is moving, there will be a difference. At least, well, which clock are we using? So that's the question, right? If we're using some absolute clock that we do not have access to, like if you're just watching the simulation, we can see what's happening, right? It feels like, so we're moving the clock over here, and now a light beam is emitted, see? And the whole thing is moving to the right, right? So this takes a while. This, because we're moving to the right side, it takes light quite a long time to reach this B. And then the backwards is it's faster because
it should be faster,
faster. But I can actually increase the animation speed a little bit also. Let me just run it again, reset it. So now, so there should be difference, right? This was slow. This took a long time when we watched from the outside, and this way back it was faster. We can even make it more extreme by changing the speed of the whole apparatus is now moving faster, right?
Yeah.
So again, we can do this. Now it should be a little even more, if we took our clocks right now, we would see this is slow and this is faster. The problem is the beginning. What happened as we need to have a clock here, right? Otherwise we can't do it. So if we just look at the animation speed really slow, we're moving the clock, and as we're moving the clock while the clock is moving, it's ticking more slowly, unfortunately. So now see the time here? It's not the same time. This is like 300.
Oh, they're not synchronized anymore.
No, they're not synchronized anymore. That's the problem, right? So yeah, sure, because it ran more slowly while we were moving it.
Yeah.
It looks like a conspiracy, but here's the numbers, and you can do the math yourself. It's not that difficult. It's a bit of a pain, but it's not difficult really if you consider that how much, because I like to use real numbers because it makes it easier for me. So I'm assuming we know where the ether is. Okay, we are assuming a certain speed relative to ether, because then you can actually calculate exactly how much it slowed down, even though it's not necessary. You can do it also in a more abstract way. But when you do real numbers, you can check it yourself, right? You can see how much the time that the clocks are out of sync, and the whole thing is canceled out when you compare. Unfortunately, you do not see a difference. So the parent speed forward and measured backwards is a two-way speed. It's there's sync offset of 60 nanoseconds in this case, but these numbers that I was using, whatever the distance was, right? Here 210 kilometers a second, whatever the speed was, it cancels out, and you cannot detect the difference, even though if we had this universal, like God-like view to the universe, like I don't know how to call it, but if we could do that, we cannot, unfortunately. But in a simulation we can, because you have a computer clock that knows what's happening. So just to be clear, I don't think there is such a clock, but in a simulation we can see that it looks like it's much slower and then faster the other way. But we cannot create an experiment because we are trapped in this universe.
Exactly.
We are made of waves. Our clocks are made of waves. Our clocks, it's just, unfortunately, it looks like a conspiracy. But then, so even if you could measure it, it would just come out the same way. It would come out the C, which is kind of frustrating. No matter what we do. So, I mean.
But the same would be if we were in water and had water clocks, right?
Yes.
The same would be like the sonar, right? We would still not be able to detect, right?
Yes,
in the
spotlight, this light here, right?
Yeah.
This is actually, I use Grok for this one, I think. This was an older version of Grok, but if everything, so basically special relativity is an emergent observation. It's an emergent theory. It's something that you would see in any wave system.
Exactly.
Any system where everything is made of waves.
Yeah.
Be rubber with rubber waves and rubber wave clocks and rubber wave circular waves.
Yeah.
Rubber
jello waves.
They would discover special relativity and be wondering, how can we detect the rubber? But if you're made of rubber waves and you have rubber clocks, wave clocks, then you cannot. So that's the thing.
Exactly.
Right. That's kind of frustrating. So the only thing we could do possibly, I think, is detect if this is somehow granular, like if it's really continuous or not continuous. I mean, maybe one day we can detect that, right? Because I think I mentioned it before that the speed of a wave at least in a normal medium, in a physical medium, is such that when you have some grain size of some sort, and the wavelength approaches that size, that grid, that resolution, it will start to slow down a little bit, right? So the speed of the wave depends on this granularity. If your wavelength approaches that size. So let's say if the universe has some smaller size, like Planck size as an example, which we don't know if it has, I would expect that, really, really blue shifted, like gamma rays would be slightly slower. That's the only thing we could do. But yeah, so.
Has that been detected?
No, the thing is, we are orders of magnitude away from detecting that. So even
no, I'm just wondering. I just remember hearing or reading somewhere that gamma rays might actually be a little bit slower. Not just the gamma rays, but they're like the super gamma rays. Like they can get the closer they get to the highest energy that they can possibly create, that the speed might be slower, or maybe they detected that.
That would be my prediction, right? If the medium has a granularity around, it won't be bigger than Planck size. I think it would have to be that level or less, probably.
Yeah.
The thing is, what if it doesn't? Maybe it's granular, but like 10 orders of magnitude below that.
Yeah, and we would never, ever, ever, ever be able to.
So some people might say, well, so that shows that we don't need the ether, right? A lot of people say, see, we don't need the ether, and that's correct. We don't need it, but we need it for the explanation, because if you get rid of the ether, and we don't need it for the math, right? Just to be clear, the math never
for sure.
Needs, we can include it, but we can always cancel it out. The thing it gives us the explanation, the mechanical, and I think hopefully I could show this is really simple explanation that special relativity and general relativity make sense, right? It's really easy to explain. Sure, if you get rid of it, then there's no explanation either. It's just all mystery and magic, and I don't know.
There's a different statement. This is something maybe James would say. There's a different statement between you don't need the ether, and there can't be an ether.
Exactly. Right? Yes.
So they're saying there can't be an ether, and because we couldn't detect it, there absolutely isn't an ether. But they're really, when they say there isn't an ether, they mean there can't be an ether, and that's what bothers me. I want to say there
clearly
can
yes, I would. This is, in my opinion, absolutely wrong, because there can be. It's possible. It's so far at least
it's compatible with.
Of course, we have other topics, right? We will have, because if we claim there can be an ether, right? It's compatible so far with general relativity. At least maybe we haven't looked at frame dragging. But, sure. There's some details, but this is. But it also, based on the papers from Robert Close, at least, it's all compatible. We have to, of course, explain. Well, wait a minute. People are claiming photons are particles, so we would have to show that we don't need particles, because if we do need particles, well, then we have the problem with, this is not going to work out, because if you have a medium and particles, well, how is that going to work, right? Mm-hmm. Because we were saying it's all waves, right? If we had some elastic medium and particles to go through it, that's not compatible, because particles, why would they have the speed of light, right? That makes
exactly.
That makes, this is then another theory on top of no.
So this is where I'll always say the problem is with the language. A language, we're using the word particle, and I think that's
totally
we're confusing or conflating two different things. Right?
Yeah, of course I used the word particle too, but that for us, like, we are big monsters compared to the small atoms. Mm-hmm. Of course it looks like particles because they're tiny. And of course we have detection events, which the click is like, oh, there's an event.
There's like a particle,
That's what the particle is. But we have to, of course, show that we can explain the photoelectric effect with just waves, and all the other things.
Yeah. And you've covered a lot of ground. So far you haven't found any contradictions. And so you've covered, like, we haven't covered it all here, but I've seen all your videos, and you really cover a lot of ground, right? And still haven't found any contradictions.
No, of course, people will say, well, you haven't gone into the details. Yes, of course, I haven't looked at frame dragging in detail. And of course, I haven't looked at the, quarks. But I mean, what are the chances? I mean, it seems to me that everything so far has been really simple and compatible. I think there's a good chance it will work out, because otherwise it would just be a huge coincidence. Imagine that, like, it looks like there's a medium, but there isn't a medium, but it's all compatible. Like, what are the chances? It would be really weird coincidence, right? I
It
mean,
would be a weird coincidence.
very
Yeah.
weird. And it's not like complicated. I'm not like adding new them. You know, you can always make a theory work if you add a lot of stuff, a lot of new
Yeah.
parameters, a lot of new, oh, I'm gonna add 5
Yeah.
dimensions, you know.
Yeah.
But
Yeah.
this is just saying there's a
You're
medium
not adding
has
anything.
elastic
You're just,
properties, you know. I think it's really elementary
it's
school
super
simple.
simple. Like it's super simple. That's
Yeah,
all
and I
you
hope
have is an
yeah,
elastic
yeah, yeah,
medium and
yeah.
you can do all this stuff.
And I
Yes.
hope people will actually take this idea and dig deeper, well, you know, figure out like, yeah, so what about frame dragging? Or maybe there's
Mhm.
something we can invent from that. I don't know. Maybe once we,
Mhm.
you know, accept that these are in fact waves, you know, maybe there's something, maybe we can control the waves. I don't know.
Yep.
It's just, I hope more people will
It's
think about this than just saying, oh no, that cannot be an ether because 100 years ago someone
yeah,
said that, you know, I was like without regarding the latest
exactly. And
experiments.
also I say one of the things I say is, there's what, 8 billion people on planet Earth, and why can't some of us say there's an ether and work on that, and other people say there's no ether and work on that, and then see, who comes up with the best model, right? So it's
Yeah.
like, I get this sort of feeling that, there's consensus and that you have to do it that way. And that bothers me because there's so many people on planet Earth, really smart people that could totally investigate one path, investigate another path, and see which one, works.
That, yes. And also, I think we're not really, we always think we are so smart. Everyone, like we think we are, oh, we are so modern and we know everything. I don't
Mhm.
think we are better than in the Middle Ages that much. Like I'm sure in the Middle Ages, people thought they were smart and, you know, they
Exactly.
thought the Earth was in the center and they
And
had
in the
empty
future will be the
cycles.
Middle Ages
Yeah,
in
in the
the
future
future
they will
sometime,
laugh
right?
about us. Of course, I don't
Yeah.
know which things are going to be wrong, but I'm sure they will. Looking
Mhm.
back from 100 years backwards, there are a lot of things, assumptions we have right now that are wrong. Maybe this is wrong too. I don't
Mhm.
know, but
Yeah,
at least we should explore. We shouldn't just assume, you know, oh, this has been
exactly.
settled. You know, the Earth is in the
Yeah.
center, whatever.
Science should never be settled. That's
Exactly. We should
science.
always
Science is
doubt.
a method. Science is a method, and you're using a method in your simulation. Science is just a method. People think science is a truth.
Yeah,
Science
it's
isn't a
not.
truth. And
Mhm.
so it's not a belief system either. So I
Exactly.
think a lot of people take it as a belief system, but science is just a method. When you look at it, scientific method, right? Science is just a method. It's not. So when you read the conclusion of a paper, it is not a truth. It is an interpretation of the results of an experiment.
Yeah,
The
at least so
discussion, right?
far, right? And then maybe
Yeah.
new evidence comes along, and you know,
Yeah.
maybe there's some
Yeah.
detail that we missed, or who knows?
Yeah. Yeah.
It will always
Exactly.
change
And
a little bit, you
the
know.
thing that I like about you, like the way you present things, and you're much more humble than most people I deal with, in that you say you still might be wrong. You're
Of
willing to
course, yeah,
admit
I know
that
I
you
make
still
mistakes
might be
every
wrong.
day, so
There are a lot of people out there that I deal with that are like, "Oh, I'm right, and I can prove I'm right, and nothing you can say can, you know, take that away from me," kind of thing, right? And it's like, I
yeah,
really appreciate that you almost every video you say, I still might be wrong.
because I know I've been wrong so many times.
And
So
I think that's exactly, and I think that's really important that we're not saying this is the way it is and this is true. It still could be wrong, but every piece of evidence, gives more evidence to the story.